Okay, we're going to look at a very special case for solving differential equation, and we're going to look at something called integrating factors. And the idea is we're going to have an ODE that is linear in y and y prime. So what does that mean? That means I'm going to have something times y prime plus something times y is something. And these things, these somethings, only depend on t or their constants. So when we say something is linear, so if for example, if I say something is linear in x and y, it means that something times x plus something times y plus some constant is 0. And these things, the a, b, and the c, do not have any relationship with with x or y. So for example, 3x minus 5y equals 7. That's linear in x and y. I can have a linear system, for example. 3x1 minus 2x2 plus 5x3 is 7. x1 plus x2 plus 8x3 is 2. Minus x1 minus 3x2 plus 7x3 is 9. That is linear in the variables x1, x2, and x3. In the case of a differential equation, if I have something like 4ty prime plus e to the 3ty equals tangent of t, that is linear in y and y prime because that, and that have no y or y prime in them. Right? So this is going to be linear in y and y prime. Okay. All right, so we're going to look at a very special case. And the special case is going to be if I have a differential equation that I can write as y prime plus p of t times y equals h of t, we can use something called an integrating factor. And before we define this, we're going to try to motivate this and talk about it and see what we can do. First of all, this is not quite as limiting as it first appears. So oftentimes we see things in a different form. We see it as being linear, and then we have to do the algebra to make it look like this. So for example, suppose I've got this differential equation. Three sine of t times y prime plus 5 cosine t times y equals log of t. It's not in this form, but it's linear, which means I can divide through by 3 sine t. So if I divide everything by that, that becomes a 1. I'm going to have a 5 cosine of t divided by 3 sine of t, y. And then on the right-hand side, I'm going to have log of t divided by 3 sine of t. And now it is in this form where that's my p of t and that's my h of t. And I can use an integrating factor on this. All right, so the first thing to recognize is that if we have anything that's linear, we can do the algebra to put it in that form. Okay? And if I have it in that form, I can play some games and use something called an integrating factor. So what the heck is an integrating factor? Before we get there, I want to just do some review here. First thing I want to do is review the product rule. And what's special about the product rule, and I'm going to use a combination of the product rule and chain rule, I should say. What's special about the product rule is what? The derivative of the product of two functions is the derivative of the first times the second plus the first times the derivative of the second. Okay, and so for example, suppose I call this, instead of f of t, y of t times f of t. This becomes y of t, f of t, y prime times f of t plus y times f prime of t. Okay, and we can immediately see this looks like a linear differential equation. And if I can play a game to take something in this form and make it look like this, I can basically go backwards. That is, if I see on the page y prime times f plus y times f prime, I can then look at that and say, that's the derivative of y times f, and now I can find the antiderivative of that very easily. Okay, so the second thing, so first thing was product rule. Second thing is the chain rule for a very specific case. If I have the derivative of e to a function, r of t, by the chain rule, that's just the derivative of e to the something is e to the something times the derivative of the something. Okay, and I'm going to use some shorthand notation and refer to that something as r prime. So putting these two things together, the derivative of y of t times e to the r by the product rule is going to be the derivative of the first times the second plus the first times the derivative of the second, which we just showed was r e to the r times r prime. It's supposed to be an r prime there. And so again, if I have something on the page that looks like y prime times e to the r plus y times e to the r times r prime, I can write that as the derivative of y times e to the r. Okay, so how do we put that to work? That's the question. So again, we're assuming that we have a linear equation, and if it's linear, I can do some algebra and change it. So the function looks like y prime plus something times y equals h of t. Okay, and I know that if I multiply both sides by e to the r, my goal is to see, is it possible for me to make the left-hand side look like that? So if I multiply this through, what do I have? I have y prime times e to the r plus p of t times y times e to the r. And then on the right-hand side, I'm just going to let that roll, and I'm going to hope I'm going to be able to deal with that later. That's going to be h times e to the r. Let me rewrite this slightly different by rearranging these terms. And the reason I want to do this is I want to make it look as much like this as possible. So this becomes y of t, e to the r of t, p of t equals h of t times e to the r of t. And my goal is to make this look like this equation. And that equation, just writing it verbatim, looks like that. And notice, this looks like that, this looks like that, this looks like that, this looks like that. The only thing that's different is those two things. If I can make these two things equal, then I'm done. And here's the great thing is that in practice what happens is you're given p of t, and I'm free to make up any r that I want because I didn't specify anything about r anywhere here. And so if I define r prime to be this, then what does that mean? That means that r of t is the antiderivative of p of t. Then I can use my chain rule and product rule in reverse. And keep in mind, I'm just using definitions, and I'm forcing this, and my goal is that in the end, I know that I'm going to end up with this so that I can do this. If I cannot do that, I made a mistake somewhere, and there's a problem, and I need to start over. Okay, so what do we have? So we have this thing called the integrating factor. First step is I need to recognize that the equation is linear and it's first order. If that is the case, that means I can do some algebra and I can rewrite the ODE so it looks like y prime of t plus something times y of t equals h of t. And again, the assumption is I know p of t and I know h of t. I can't change those. But I can multiply both sides by any function e to the r of t, and it's going to be okay. And if my r prime is equal to p of t, just defining that, right, then life is good. And I can basically, I know in advance that I'm going to be able to do the product rule backwards to make things work. So what does this say? This says that r of t is the antiderivative of p of t. Once I've done that, I know that the left-hand side is going to look like y prime of t times e to the r plus y of t e to the r times r prime of t. And that's going to be equivalent to the derivative of y times e to the r of t. Again, I did that, I know it in advance. And at this point, I can just integrate both sides and move on. Okay, so there's some amount of faith here that I can integrate the right-hand side, but I know that the left-hand side is going to be straightforward. So let's see if we can do one example, and then we'll do some more examples in a separate video. So for example, y prime equals minus y plus t. Let me rewrite that so it's a little more clear. Okay, suppose this is given to me. First thing is recognize it's first order and it's linear. Okay, that means I can rearrange the terms. So let's see, first order, it's linear, and if I add y to both sides, it is now in the proper form. It's something times y prime plus something times y equals some function. In this case, those functions are 1, right? So I already have y prime plus 1 times y equals t, which means then that my p of t is 1 and my h of t is t. Okay. All right. So the first thing to do is I second thing is reorder, and I have it in the form of y prime plus y equals t, and I've identified what p of t is. And notice there's always got to be a 1 in front of the y prime. The integrating factor is just defined to be e to the r of t. Okay, so I'm going to multiply both sides by that. I'm going to call that my integrating factor. And I know that r prime is equal to p. So r prime is 1. And if I take the antiderivative of both sides, this is going to be t plus c. Here's the thing. I don't care what c is. I'm just going to let c be 0 because I only need one solution. So I'm just going to say, let's let r of t be t, and I'm going to ignore the constant for now. So what? So now I'm going to take my equation. I'm going to multiply everything by e to the r of t, which in this case is going to be e to the t. So what do I had? I had y prime plus y is t. My integrating factor is e to the t. So I multiply both sides by e to the t, and I have e to the t times y prime plus y times e to the t is t times e to the t. And notice the derivative of that is right there. Okay. So by the product rule, the right-hand side, or sorry, left-hand side is y of t times e to the t, and it's going to be equal to whatever the right-hand side is. This is by design. I defined my r of t so this would happen. If this does not happen, you did something wrong. Right? If you cannot do that, if that is not true, you made a mistake somewhere. And the whole point of this was to take this step right here. The whole reason behind integrating factors is so I can get to right here. And once I have this, I can integrate both sides and then solve for y. All right, so what am I going to do? If I take the antiderivative of both sides, the antiderivative of the derivative is just that function is equal to that. Okay, and again, this is by design. This should always be the case. If you cannot do that, something went wrong. And now at this point, it's just a matter of faith that I can do this. So I got to figure out how to do this integral. And now it's a Calc 2 problem, which makes us happy. We can finally use our Calc 2 stuff because they said we'd never use it. In this case, what am I going to do? Well, I've got t that, so this I can't do the antiderivative directly. There's no u substitution. So let's try integration by parts. I would love to take the derivative of t, because the derivative of t is 1 is going to be nicer. And I'm going to hope I can take the antiderivative of what's left. So for my u substitution, I'm going to decide let u equal t. And once I do that, basically everything else is chosen for me. Because that means whatever's left is my dv. And I'm hoping I can take an antiderivative. Well, the antiderivative of e to the t is just e to the t. And the derivative of u is 1. So this becomes u times v minus the integral of v du. And the integral of e to the t is just e to the t. I got to be careful as I'm going to be off by a constant. Notice up here, I should have had a constant, but I left it off because I knew I had a constant floating around on the right-hand side. And it's going to just come out in the wash. So what do we have? At this point, we now have that y of t e to the t is equal to the antiderivative of t e to the t dt. We just decided that's e to the t times t minus e to the t plus a constant. And just like before, it's really important that we recognize when the constant pops up and why. Now I'm going to multiply both sides by e to the minus t, because I want to get rid of this. I want to isolate y of t. So this becomes t e to the t times e to the minus t minus e to the t times e to the minus t plus c e to the minus t. That's just 1. That's just 1. So I get that y of t is t minus 1 plus c e to the minus t.